The Open Hardware MiniConf. We have a really exciting presentation this afternoon. We have here Brian Faith and Tim Sachs from QuickLogic. Brian is the CEO and Tim is the CTO, I believe. And they're going to be doing a talk today about FPGAs. And so if I tried to explain anything about this talk, I would do a very bad job of it. I think it would be best if I left it to Brian. So Brian, please take it away.
Thanks, Jonathan. It's great to be here with everybody coming in from the United States. Joining me is Tim Sachs, our CTO. He's going to lead us off, and then if there's time, then I'll come back at the end. So, Tim?
Okay, great. Thank you, both of you. So what I'm going to talk about is a small device we built. So here's a board we have, a QuickFeather board, we call it. It's a feather form factor. We're working on a QuickThing version of it. And on it is this small device, which was designed for wearables. It has an M4 processor in it, a little piece of FPGA, some memory, microphones, that kind of thing. And what I'm going to show you is an evolution I went through this year. We decided to do a Hackster.io event about environment kind of things. And we decided to do this right at the time when California was burning up. So I got this blue box, which is from Adafruit, which is a PM2.5 sensor, and I hooked it up to a QuickFeather so I could see what the air quality was, and it was terrible. And then more recently, I decided, well, that's kind of fun, but it would be more fun to add more stuff to it. So what I did was I took another QuickFeather, hooked up to another one of these boxes, but I added this unit here, which is a M.dot LoRa transmitter. And the blue box over here is the LoRa receiver. So I'll show you the process I went through to hook this up and the role that the FPGA plays in this. So if we could please switch to the screen share. So we started, when we started on this chip, we were one of the classical proprietary companies, but we've been transitioning more to open source, actually going 100% in on open source. So on our QuickLogic website, you will see a couple of things. You will see a Quark SDK, which is the thing that runs on here. You'll see a QuickFeather board, which is the documentation on the board I just showed you. And you'll see a QuickLogic FPGA toolchain, although that's been replaced now by a SymbiFlow toolchain, which is an open source toolchain for programming the FPGA. So how did I set this thing up? Well, screen's not switching. So I created and I have, it's in the Quark SDK. So if you go into that repo and have a look, you can find it. There's a README in there, and it explains. It goes through this little Adafruit box. It shows you all of the pinout on it. It shows you how you would make the decisions and which pins to choose to hook up and so forth. Turns out this particular version hooks up with the UART. So I have this bunch of cables essentially just supplies power. So here's the README for that application, showing the box, showing the pinout, so that it's showing the QuickFeather, how it connects up, and then the thought process on all of the pins and how to drive it, how I figured out which pins to use, because as common with most parts, every pin can be used for several functions, and they never quite line up the way you would like them to. So I stepped people through all of that. And then the result of all of this then is, of course, some code. And the interesting thing about the part is that you might have noticed that we have a USB connector and a USB cable, but we don't have a USB peripheral in there. So what we do is we program the FPGA to be to do the USB function. So if you look at our main function here, we set up some clocks. We load the FPGA with a bit stream, and here's what the bit stream looks like. It's kind of human inreadable, but that's life. And when that bit stream's loaded, then we can run USB serial init, and we have our serial port hooked up all these messages then pop out on the screen. And then we start the debug, the monitor task. So the monitor task, as you'd expect, looks like this. So essentially, it issues a reset, brings the device out of reset, and then it sits here just reading the bytes from the device. And as it reads the device, if I've set this variable, it prints out the PM2.5 standard to the screen, and I can see it on the screen. So now what I'm going to, and that's all handled with our command line interface. So we set up an ability to toggle variables and stuff like that. So here we go. Just got to find the right screen here. Yeah. So here I'm connected to that first quick feather. I say help. It says, hey, you get to do these things. So I'm going to say show 2.5. And it starts printing out the PM2.5. There's also an LED on the device, which you might have noticed blinking. So I can blink the colors according to the AQI. So I can make it, green, yellow, red. So that was the simple one. Now, how do we get to LoRa is an interesting question. So the issue, with LoRa is now the LoRa device also hooks up with a UART, and the quick feather only has one UART port on it, and the serial port for the USB. So I need a third UART port. So how am I going to get that? So the way we do that is by using the embedded FPGA. So this is one of the uses for the embedded FPGA. Another use is for running high-speed peripherals. So we did some work with megahertz kind of ADC, and we had to run SPI at a megahertz, not the SPI bit rate, but trigger SPI transactions once every microsecond to read the ADC. We used the FPGA for that. So in this case, what I do is we have some gateware, and we have a 2 UART piece of gateware. I need the 2 UARTs because if I'm using the FPGA for the UARTs, I can't also use it for the USB serial. Why, you ask, is that true? Well, the open source code right now doesn't get us enough performance out of the FPGA to be able to use the open source FPGA compilers to run the USB. That's something that we expect will get fixed in the next few months as the open source software improves. So we load 2 different FPGAs into 2 different UARTs into the FPGA. One of them connects to the command line interface. The other one connects to the PM2.5. And then the third one I use for snooping, for talking to the LoRa. And then I also have another physical UART so I can snoop on all of that. And then, of course, the LoRa radio talks to this multi-tech box, the big blue box I showed you. And then with Ethernet, we can go talk to that. So what does that software look like? So let's kill this. So the main program changes just a little bit. So we set up the clocks again. This time, though, we don't load we load the FPGA, but we have a different .h file. So now we're loading top.bit, which actually has the USB stuff in. We configure the USB, and then we start a LoRa task and we start a PM2.5 task. So top.bit.h, again, not very readable. ASIC FPGA, this is all in Verilog, not the most friendly language in the world, but that's the way it is. And the thing we really like about this is the build process. So I ran a build just a few minutes ago, and you can see this is sort of a conventional build where we go through and we enter the various directories. So we enter the startup directory, make it, I've already done it, so nothing to do, HAL, FreeRTOS, so on and so forth. And then down here, you'll notice that we dive into this directory called Gateware with S3 FPGA 2x UART. We run QL Symbioflow, which is the open source FPGA compiler that munches on this string of Verilog files and creates this top.bit file, which it pushes into the right directory. And then the compile continues and incorporates that bit stream. We do the link, and then when we program the part, which I did down here, program the part, now I've got my UARTs in there instead of my serial USB. So you can sort of see the power of this now integrated method where you can treat the Verilog just like you treat C code and bring it in there. Now, it's a little wasteful to put the bit stream into the memory and load it from there. So there's another option to program the bit stream into the flash device, and then you load the M4 code from the flash device and you load the FPGA from the flash device, so you don't take the memory up to do that. So now let's look at how we changed the code. So the 2.5 task now, I have a variable set where I say, well, do you want me to transmit the 2.5 stuff? If you do want me to transmit the 2.5 stuff, I write it in a particular variable. I set this thing called fNewData true. And then the LoRa task, which is running in parallel, he sets up, tells it to join. Notice how we use AT commands. They've been around forever, probably will be around forever. If there's new data, it creates this AT command that includes the data, the 2.5 level, sends it out over the UART to the LoRa device, and echoes it to my console, gets the response back, echoes that to the console, sets that new data false, waits a while, and then continues in the loop. So we've got these two tasks running together. The PM2.5 task is monitoring the little PM2.5 device, and every 10 seconds or so, it spits data out to the LoRa. The LoRa transmits it, and it shows up somewhere else most of the time. So we'll have a look at that. So let me just pop up several windows here. So this is this screen, bottom right here is the console screen. So you see that every now and then it's saying AT send 0. So right now my PM2.5 level is 0. So my room's nice and clean. And then it gets back, it's the echo. So the M dot echoes, yep, I saw it send and I'm okay. This is actually the screen on the left here that I'm bouncing up and down is the one that's tracking what's actually going to the LoRa device. So you can just see I send the AT plus send 0. You can see my air quality is deteriorating. It went to 1. And then this top screen is the SSH screen over to the LoRa receiver. And it's printing out all of this mess of stuff. More information, tons of information, tells you what frequency it's running at. The critical thing in here is this little phrase data. So you'll say it's up here it's saying data MA equal, and down here it says data MQ equal. So what's going on? So if we look at the MDOT, they do a base 64 encoding. So it turns out that MA is the way you encode the ASCII character for 0. MQ is the way you encode the ASCII character for 1. Of course, the nice thing about this is that they use Linux. So what I can do is take that stream, and I have a nice little awk file here that I just entered all of these tables because I was too lazy to actually try to write the base 64 decoder. So my little awk script reads that string coming out, strips out the data field, and then runs it through this transformation array. And with any luck, if I can go back there, now what we see is what used to be this big string is translated into nice little information. PM2.5 is 0, and then I put in the base 64 decoding just so I can see whether everything's working right. So that gives you, I hope, a little insight into what we can do with the QuickFeather. It gives you a little insight into what you can do if you have FPGA built in. Our vision going forward is to add more FPGA and by using open source tools to make it run faster. One of the challenges I believe today with FPGA is all of that stuff that's really designed for hardware engineers. Hardware engineers are used to a very expensive, time-consuming world, so they're very patient with compilers. I find most software engineers are a lot more impatient and want things to happen quickly, and we would like to enable that for people, and we would like to tie it in such that you can actually use the FPGA for more interesting tasks like pre-processing data. So we do things like digital filtering in the FPGA, so we offload the CPU. We do convolutions when it comes to things like machine learning. We push the convolutions off into the FPGA. We see a whole world of that building up and developing. So that is my brief demo of our hardware and where we've gotten so far. Brian, over to you, I think.
Yeah, I can do some sharing of our journey to this point, and then I'm sure we'll have time for questions so that people can ask you, Tim, questions on all that cool stuff you built out of it. Okay, so the title of this was actually Our Journey from Resistance to Adoption, and this was actually, we just wanted to share with everybody how we got to this point, because most programmable logic companies sort of resist doing anything in the open source domain. So not to market this at all, QuickLogix started as a programmable logic company. We have devices like what Tim was talking about that have combinations of microcontroller and FPGA on the same chip, and then we do things like the QuickFeather board and soon to be others that are all open source. So we started as a company 30 years ago, actually, and 60 companies have come and gone in that space, in that time frame. And a lot of them have actually failed. And it's an interesting trivia question, but almost in every case, it's due to software or lack thereof. And so for the ones that have lasted, it's really about having robust software. And that software is actually a walled garden. So in most cases, FPGA companies like having people use proprietary tools because there's lock-in, and then you're kind of stuck. So we took a very random path to get to this point, and I bet a lot of people that are watching this actually recognize that face there on the slide. But this was an incredibly random path that led to this point. And if anybody needs a lesson in persistence, you can go talk with Tim Ansel, because he's a persistent guy. So, you know, it's actually incredible to go out and talk to these different folks in industry and in academia to realize how far open source tools have come to the point where Tim can knock out that demo in less than a weekend. But we've talked to Toronto, which is a key part of this whole open source FPGA tool. They started the place and route component of it called VPR. We've done test chips with ETH and Zurich with RISC-V processors. University of Utah is heavily involved because they're doing things around FPGA IP core creation with open source tools. And then Tim actually, we still were resisting this, by the way, and Tim suggested you need to go to this FASE event in the OR conference in Europe. And so Tim and I went there, and we were just blown away at the quality of result of the open source FPGA tools. And it really sort of shone this light on the open source domain for us. And that's really what changed our mind. And so we were going from this resistance of, no, we don't need to do anything open source, proprietary is lovely, into this moment of actually taking that leap. And as Tim said, all in on the open FPGA tools. So that kicked off this whole collaboration with Google and this company Antmicro in Europe. And that basically took all of our proprietary information on our devices and our architecture and moved it into the open source domain. So that meant that we had to sort of lift up a little bit the curtain on these technical details that we would normally hold back, so that tools like SymbiFlow, which encompass the synthesis and placing around and bitstream creation, can actually effectively target the device architecture. And we didn't stop there. So we did things like Zephyr, which is an RTOS for the Cortex M4. And then Antmicro has a tool called Renode, which allows you to basically emulate the whole chip in software and not even have a board. And then we have all these different open source boards now that are available. So you can get them from QuickLogic, or you can go to the GitHub repo, get the information to do your own equivalent board. Some of these are actually unreleased. They're going to be coming soon. And they're pretty interesting to build useful applications off of. So once we got to that adoption point, then we just sort of off to the races. And joining all these different alliances that are really focused on open source tools, open source software, and building chips on that. And like Tim said, we're all in. So we're going to continue to do this in the future. Almost everything we do is going to be based on open source software and hardware. And it was really cool because we had these things out there for some time, and Tim was doing these really neat demos around the PM 2.5 sensor and other things. And then this company that was using our devices built this module, and he sent me this video and he said, hey, check this out. You don't even need a PC anymore to do FPGA design. And having been in the industry for 30 years almost, it was incredible to me that that was even possible to do that without a PC or a pretty high powered workstation. And he basically sent me these videos where he'd taken the SymbiFlow open source tools, because it's open source, and he got it running on an Android phone. And I guess conceptually that makes sense because there's actually a lot of horsepower on an Android phone now. But just to see that actually working in real life, basically taking the same systems that Tim has shown you and designing, changing the FPGA gateware, and then programming that through the FPGA tools using a smartphone, which is, it blew me away. And then similarly, they actually use the Raspberry Pi. So Raspberry Pi now can also run the same FPGA place and route tools. You can change the gateware, program the device back on that QuickFeather board. So again, it's just sort of a glimpse into the future, and it kind of makes you appreciate, like I have young kids, they could actually use these things now on their tablets or Chromebooks or whatever they are. They're not limited by, you know, me going out and buying them a $1,000 computer to go run place and route. So this, I really think this is sort of disruptive and change. It's going to change everything as far as who actually can start to do design with these types of devices, some types of technology. And it's not limited to QuickLogic. This is not a sales pitch for QuickLogic. It's really just the idea that this is sort of democratizing this technology is awesome. So what can we do together? I think Tim opened this up with talks about the fires in California. So we had lots of fires in California. I think there were definitely more than 2 million acres, I think, burned in California just this summer. It was incredible. And I've read that there's been a lot of fires down in Australia as well. So what we've actually done is created this contest that I think can actually sort of help out the world in the climate. And that's basically taking the QuickFeather boards and then doing neat things like what Tim is doing, where you can attach different sensors to it that aren't on the board, use the open source tools, and just see how creative you can get. So we did this contest with Hackster.io. And so I thought about it too late, but we should have actually sent a bunch of boards down to Australia. So you folks could have had boards while we did this conference and did this training. But I didn't think of it fast enough. So, but I will send the first 20 people boards. So just email that email address and I'll get you a board, and hopefully you can get the tools and start designing as well and have some fun with this open source tools. So that was really quick. I've done this presentation in a lot more time, but I want to condense it for this. This is, I think the persistence of the open source community is awesome. The passion's there. And we're seeing it now. And so we are fully committed as a company to the open source toolchain for FPGAs now, no longer doing the proprietary stuff. And we did it because I think the tools are ready, and not just ready for our architecture. Again, this is not a sales pitch for QuickLogic. I think they're ready in general for many architectures. And as long as companies provide information to the open source community, those tools will yield good results. Resistance is futile in this case. So I think pretty soon we're going to see open source tools be the norm and not the exception. And that is it.
Fantastic. Okay, thank you very much, Brian and Tim. So there are a couple of questions that popped up in the chat, and I have a question myself. So Tisham asked, is there a sample gateway or ASIC recommendations for the high-speed ADC usage with the QuickFeather?
Tim, do you want to take that one? If he's
Tim is not currently added to the stream.
Okay, well, I can take that. So yeah, we actually have Gateware, an example code for connecting. Oh, there's Tim.
Yeah, I could take that. Actually, if you look in the Gateware repo, you will probably.
To release Tim again.
Yeah, I'm not sure. Looks like we might have his audio occasionally.
Well, the short answer is yes, we do have example code.
Okay.
I think it's in the examples directory off the GitHub repo that we have.
Okay, so that's the example. The specific question was about high-speed ADC, so you've got examples related to that.
We do. An
Fantastic.
example of connecting it to QuickFeather.
Yeah. Okay. Well, that sort of ties into what I was going to ask, which was whether you have examples of blocks of code, because in Tim's example, he mentioned adding a third UART, which implies taking a chunk of functionality and adding it into the project,
Right.
which is the sort of thing that gives the amazing flexibility that you can achieve with FPGAs. So part of the value that you would provide, of course, is making that easy for your customers. Do you have a library of those sorts of functions?
We have a library of functions, and it's something that's going to grow over time. We actually have a lot of gateware that we've sort of kept internal for a long time, and we need to sort of put that in the right way for the open source community. So the simple ones are like different GPIO that you can do in the FPGA, the UARTs, the multiple UARTs, the mixing and matching of those, the USB device that Tim was talking about. And then we actually have some internal gateware that we're going to start releasing, which uses the eFPGA not for simple connectivity things like UARTs and GPIO, but more for offloading things from the processor. So it sort of moves it into an offload or an acceleration engine from the Cortex M4. Totally different use case, but we actually have examples of that running now that we're going to start to open source as well.
Oh, that's great.
Yeah.
So, yeah, I can imagine all sorts of applications for that, related to crypto or whatever people might want to use. So are there particular applications or projects that you have seen people build with the QuickFeather already?
Yeah, so actually, it's pretty interesting. So if I just I don't know if my slides are still showing, but I can just speak to it. So that one where we're talking about the Android phone and the Raspberry Pi and using that to do the design and programming, they've actually built a module. Oh, the slides I was showing, or now they're not. They actually built a module that was rectangular in shape, but much smaller than QuickFeather, that they could actually put memory on and the EOS S3 device. And they're selling that as an open module to people that want to sort of integrate that at the board level without, having to buy the big QuickFeather device. So that is already happening, and they're targeting wearables. So they've actually made it pretty small, so you can actually put it into a wrist-worn wearable or some type of a necklace device, because not only is it small, but it's also low power, so you can kind of get away with that for battery-powered applications.
Okay, so that's another interesting aspect, is the power requirements. So for people that haven't done anything with FPGAs before, could you maybe speak a little bit about how the power requirements of something like a QuickFeather compares to a more traditional microcontroller?
Yeah, so the EOS device itself has, I think more than 30 different power islands. So if you're only using the microcontroller, you're actually going to find it to be of similar power as a low power microcontroller. The core voltage is like 1.2 because it's at 40 nanometer. So microcontroller alone is in that range. Our FPGA is not sort of the classical like data center style FPGA, so it is actually designed for low power. So in general, the part itself, when you're running full bore, is going to draw easily less than 10 milliwatts. And there's a lot of applications for always on sensing, where you're doing microphone listening, classification, types of examples where you can actually run it probably like a 10 MIPS kind of model for less than a milliwatt.
Okay.
And the FPGA itself is like, standby is like 50 microwatts. And if you run it at 10 or 20 megahertz, maybe you're drawing around a milliwatt too. So it's actually, you can do some pretty interesting things with a battery
Yes.
with our device. You won't find it in the data center, so it's on the other end of the spectrum, but that's fine. We know what we're
Sure. And you're certainly not taking on a big power penalty by doing it. It's definitely something that can be built into a small device. And there is a question from Paul McCarris, who asked, how big in number of LUTs is QuickLogic's largest FPGA?
So the largest, we have many different technology FPGAs. We have SRAM reprogrammable, we have anti-fuse, and then we've also done some SRAM reprogrammable on an FDSOI process that's an eFPGA, so it's a licensable IP. So this device it's 1,000-ish LET4s equivalents in our logic cell. We have anti-fuse based devices that I think go up to around 8,000 logic cells, which are basically equivalent to a LET. And then on some of our newer embedded FPGAs, we have ones that go up to like 32,000 LETs. And then we're actually, I put this in backup, so I can actually put this on my slide now, if you can go back to the slide. But this test chip that was done by the ETH University in Zurich, so this one has around 32,000. No, sorry, this one has around 8,000, but there's another one that's coming that we're doing with the Open Hardware Group that'll have quite a bit more of those logic cells or LET equivalents. That's going to be tightly coupled with a RISC-V processor and a bunch of peripherals. So it could be used sort of in all those different use cases I was mentioning earlier. But just generally speaking, we're focused on the sort of lightweight FPGAs where they're not too dense that you couldn't use it in a low power application.
Yeah, sure. Okay. Well, related to that, I believe you also have example. So the QuickFeather itself. Ultimately, what you are wanting is for people to build your FPGAs into their projects or products or whatever. So the design for the QuickFeather, I believe, is open source as well. Was that done in KiCad, or what tool is that done in?
I think it was done in KiCad. Yeah.
It was
great.
Yeah.
Fantastic. So that's a good thing for people to get started with if they want to look at an example of how the FPGA has been implemented on an actual board.
Yes.
That's great.
Yep.
There was a question from Paul Schultz, who said, this is talking about the example project with LoRa. He said, where is the LoRa processing done? Is it in the FPGA?
No, it's done in the M.dot module.
Yep. Okay. And there is also a question from Eleanor, who said, the QuickLogic website talks about support for Windows 10 and Linux. Does that also cover Mac OS because of the Unix-based tools?
You want to take that one?
Yeah. So basically all of the new open source tools run on. You can run a virtual machine on a Mac OS. Ubuntu 18 seems to work fine on the virtual machines. In fact, I run Ubuntu on my Windows machine. Virtual. Yes.
Yeah. Okay, great. Now, just putting the call out to the live stream here, we've got a couple more minutes available. So if anybody does have questions about FPGAs or QuickLogic and their journey to open sourcing all the things, which is seems to be what they're intending to do, please drop questions in the chat while we have the chance. This is a great chance to be able to ask questions directly and get the sort of information that you don't normally see. Oh, and the other thing I should point out is Brian was recently on the Amp Hour podcast with Chris Gamble and Dave Jones. So if you want to learn a little bit more about that and the journey of how he and Tim Ansell came to the conclusion that they needed to a tool chain, go and check out that episode. I think it might be the second most recent episode.
Yeah.
Brett Downing said, how quickly can the application processor replace the FPGA bitstream?
Yeah, so this in the QuickFeather, it's not actually reprogrammable in the sense of you have to power it down and power it back on because of a bug. Hate to say that, but the actual programming time itself is on the order of like maybe 10 milliseconds if you can supply the data to it that quickly. So in the ETH one, we can reprogram it time and time again, and it's on the order of 10 milliseconds.
Wow, that's not very long. Okay. I don't think there are any other questions. Oh, hang on. There is one. Hasjim has said, what sample applications have you seen end users use these FPGAs for? And actually, just as to expand on that a little bit, how long has this FPGA been on the market? I mean, if it's brand new, then you wouldn't have very many examples out there. So when was it released and what have you seen so far?
So it was actually released in full production 2 or 3 years ago. But when we first released it, we were focusing just on a very narrow set of people with proprietary tools. So we didn't even have our data sheet on the website that somebody could use. It was really locked behind NDAs. So this approach has only been since earlier in 2020, actually springtime 2020. So since then, we have a lot of different FPGA use cases. So for example, millions of these are actually shipping in certain smartphones right now. And some of the PWM, Jonathan, when you were talking about PWM earlier, so we're basically implementing a PWM in the FPGA so that it can communicate with an IR LED for infrared transfer out of the phone into for some elder applications. So that's one. In a hearable application, when I say hearable, I'm talking about a Bluetooth headset. So there's a voice software company that's doing some voice recognition software, and some of the math functions of their software were pretty intense. And so they sort of capped out the MIPS that were available in the part, and they asked us if they could use the FPGA for offloading that. So they actually, it's either FFT or FIR filter we're actually doing in the FPGA that's offloaded from the Cortex M4. And that's a great example actually of the offload capability of that on chip. The other ones that we're doing are like Tim was showing, where you're mixing and matching more simple interfaces like UART, SPI, I2C, and general purpose IO in those areas. That's for this chip. Tim has actually shown that you can do things like human presence detection with some really low power CMOS imaging sensors like from Himax. And so that can actually run. So it's running basically TensorFlow Lite neural nets on that whole chip. And we have some multipliers next to the FPGA. So you can actually offload some of the convolution heavy lifting math from the processor on the FPGA as well. And we've demonstrated that. That's not in a customer production yet, but that's basically a use case that's sort of demonstrated at this point. And hopefully a customer will take that to production.
Okay, great. Just following up on the question earlier from Tisham, he asked about the example ADC gateway code, and he has found it in your examples and he's linked to it in the chat. So for anyone else that is interested in that, check the chat in Venulus. It's right there, and go and see QuickLogic's example code. There was also a couple more questions are coming in. Andrew said, for people who are new to computer science and hardware dev, how long could it take to gain a functional understanding to use these technologies?
Tim?
Yeah. I think we have some examples that show things, and I think, if you think logically, and most engineers do, it's not that hard to figure out how to use the Verilog and so on. The biggest problem with Verilog is it was written by a hardware guy who didn't understand programming languages. And so it's kind of like C, just enough that you'll keep making tons of mistakes. But when you get through that, the basic logic of doing it, it's really not that different than writing any tight embedded code or kind of thing. So it should only take like a week or so of playing with some of these examples to figure out how to do it. And that's the cool thing. And that's the cool thing about having it.
It depends on your background as well. If you're a complete beginner, then it's a big hill to climb.
Yep. But I think the cool thing about having it in something like QuickFeather and open source so everybody can use it is you can take one of our examples, and you can break it. You can start changing it, right? I don't know how most people learn, but the way I learn is I like to start with something that sort of works, and I improve it, which usually goes in the wrong direction to begin with, and that's how I learn, right?
Yes, and there's some, I can't remember the wording of it, but there's some saying about the way is long if you follow the instructions, but it's short if you go by example. Something like that. I just butchered that. There's a question from Jashank. Sorry, I hope I got the pronunciation correct. How long did it take in time and dev effort to get from we would like to use open source tools to we can generate usable bit streams?
Oh, so firstly, we did not do it alone. We did it with the folks on this slide. And I would say that was probably on the order of a year, right, Tim?
Yeah, it was, well, it was a year to where we released it, right? Having bit streams that we could run internally was probably only like 4 or 5 months. And
Yeah,
that's leveraging on a lot of work from VPR
right.
and XPNR and the stuff that's being done by, reverse engineering Lattice and reverse engineering Xilinx.
Right.
It's a good infrastructure there to build on.
That's true.
Great. Yeah, that's really where you start to see the benefits of the open source community and the collaborative efforts, which is brilliant. That's the whole story right there.
Exactly.
Yeah. Okay. Well, I think we're just about up to our time limit. We're approaching the afternoon tea break now in about a minute. So, Brian and Tim, thank you very much. FPGAs are a technology I haven't really done anything very much with myself, but I am fascinated to see what other people do and different approaches to solving problems with different technologies. So it's been very educational. Thank you very much for coming along.
Thanks for having us. It's been a lot of fun.
Yes, thank you.
All right, so for everybody on the stream, we will see you back here at, what time will it be? 3:45 Melbourne time, whatever that translates to, so in about 25-ish minutes. And we will have a talk about an amazing Commodore 64 computer reproduction, which is also an FPGA story. So go and grab yourself a drink, and I'll see you back here very soon.